Hi, welcome to part 2 of this timer series. Now, there was going to be a part 2, but I didn't really show you how to set the 8-bit timer, and I sort of glossed over a lot of the maths. So I've set my scope up today, and I've connected my scope to the computer so I can get some screenshots. This is currently the 8-bit timer, and as I explained at the end of the other video, this timer low will count up to the predefined value you have set in the timer high register. That's all very well and good, but how do we find the value we need to get a specific interrupt? That's what I'll show you on the screen. I've done a Word document, and as always, when you do some calculations, get something like a counter or a scope and check your measurement. I always like checking it over 60 seconds. I'll show you why sometimes it's better to use the onboard display or an onboard function rather than use a scope. There's something that will throw you off. Well, I've copied some of this from the C file because the C file doesn't zoom in very well with this capture software. So 8-bit timers, frequencies and periods, specifically the Pic18F27K42 used in the demo. I say specifically because unlike many other microcontrollers, this timer, or certainly timer 0, needs both registers, the timer high and the timer low, to function as an 8-bit register. As I explained in the first video and at the beginning of this video, timer 0 low register counts up to 255. When the timer high register gets to 255, if it isn't there already, it rolls over and gives us our flag, and that's when we can do something. So there's the interrupts I discussed the other day. On the interrupt, you get the flag. The first thing you should do is clear the flag. That's what I'm doing here, clearing the flag. Resetting the timer high and timer low register to the desired values. I'm inverting on this board RA6 with that little squiggly line. It's called a tilde. I think it's spelt tilde, but it's pronounced tilde. I'm incrementing a counter. But this time, when the counter gets to my desired value, I'm putting the value in here, so when it gets there, it disables the interrupts. So that means that on the display, the timer will stop counting and you can focus on how long it took to get there by looking at, say, a timer on a mobile phone. Right, so on this 18F27K42, it's got 2 registers, and we need to use both of them whether you're using 8-bit mode or 16. This is a brief description of what the bits do. So timer 0 control 0. I say timer 0. There were 7 timers in this microcontroller. Bit 7 turns the module on. 6 isn't used. 5's read only. 4, that's important. Bit 4, shown there in yellow, hopefully you can see my mouse moving, is a 1 if you want it as a 16-bit timer, or 0 if you want an 8-bit timer. This video is solely about an 8-bit timer. So bits 3, 2, 1 and 0 are the output post scalars, and I gave you a brief demo in the first video. If you set the post scalar to 2, which is actually 1, it's that last bit here, or which is actually set to 1 here. If you set it to 1, it will count to that 255, or whatever is in the high register. It will count to that number twice, and this chip has got a maximum of 16 to 1. So the second register is this timer 0 control 1 register. So bits 7, 6 and 5 are the clock source. You've got multiple options. Today I'm using 101. So medium frequency internal oscillator 500 kHz. So bits 7, 6 and 5, we go down to the register, shown there in yellow, 7, 6 and 5, 101, 101. If you want 31 kHz, 100, or you could have the 64 MHz oscillator divided by 4, which is 010. So 7, 6 and 5 of the clock. 4 is a synchronization bit, whether you want to synchronize it with your initial clock or have it free running, I guess. And then 3, 2, 1 and 0 are the clock prescalers. That essentially divides down the clock. If I chose a low frequency 31 kHz oscillator and divided it 32,768 to 1, we'd get an output which is close to 1 second. So for our project today, we will select the internal 500 kHz clock. 500 kHz, 500,000 Hz. The period of 500 kHz is the 1 divided by the frequency. Ours is 1 divided by 500,000, which equals 0.000002 seconds, or 2 microseconds. Didn't show you the other day on the calculator, little shortcut. So 500,000 Hertz, use this 1 over x here. There's our period. If you click this again, puts it back to frequency. I didn't know it did that. So a period of 500 kHz is 2 microseconds. If we load the timer H register by 255, it will count 256 of those periods, since it counts from and includes the 0. So that's why when you're using Windows calculator, use 256, not 255. If we want the slowest count in our timer, we use 2 to the 8. I showed you in a video a few weeks ago. The standard, go to scientific, 2 to the power of, so there's y over x, 2 to the power of 8 equals 256, times the frequency period, which was 2 microseconds. So cancel, go back to standard, it's clearer. So 256 times the period, so times 0.123456, 2 microseconds, equals, that gives us a period of 512 microseconds. Now, knowing this flips it back, that's 1953.125 Hertz. Got a little note there, so 2 to the power of, I said the other week, that's a correct, means to the power of, in case you don't know. So to check our results on like the display and an external timer like a phone, we need to know what to expect over a given period. I always like to choose 60 seconds. So 60 seconds divided by 512 microseconds equals 170,187.5 counts. 60 seconds divided by 512 microseconds, so 0.123, that's all in milliseconds, and then 512 microseconds. That's what the counter will come up to. So I can copy this. I haven't got my C file open. I can copy that and put it. Oh, it's already there. Put it in this. Put it in the C file in here. So when this counter gets up to 170,188, because I've rounded it up, the counter will stop, and I can just, when that stops, glance over to the phone. How long did it take to get there? Just to confirm our timer is set to the right frequency. So it says here, our port on time will be 512 microseconds, see scope. There we go. So this is my Keysight Bench View software. Comes free with scope, so that's handy. So this is our 500 kHz oscillator, no prescaler, no post-scaler, counting to 255. And you can see there we've got a period of 1 millisecond, roughly. But what did I say? In theory, the maths, and the maths never lies, if everything is as it is, we should have 512 microseconds there. We've got 517, so it's slightly slow. See the width there. And that's a live view, you can see it obviously moving. Anyway, so there's our pulse width, 517, 518 microseconds. so it's a little slow, it's a little wide. But obviously that 500 kilohertz internal oscillator isn't a factory calibrated. I'm not using a temperature compensated oscillator or anything expensive, so it's not bad. Something wrong with this frequency, but I'll go into that later. Anyway, that's the scope view. I did a capture of that scope view earlier, and in case you don't know, so that's the pulse width there, and it said it on the scope. That's the period, the on time and off time, that's the period. Frequency is how many cycles per second. So 500,000 hertz, 500 kilohertz, or 500,000 cycles or periods per second. There's a little bit of trivia down there. For much of the 20th century, 500 kilohertz was the primary international distress frequency. Bit of trivia, in case you didn't know. So we previously had this 518 microseconds. It's meant to be 512, but got a note here. If you add a 2-to-1 post scaler, it will count to 255 twice before rolling over and giving us our flag. So that will effectively double our pulse width. So I've got a note here, show on scope, pulse width of 1 millisecond. This is currently at 517 microseconds. So if we double the output, it should double this pulse width. And I've got my C file open now. So if I go to the TOCON register, post scaler, so 2-to-1, I put a 1 at the end. So I put a 1 there. Build and program. There we go. Pulse width, yes, just about doubled it. So we had 0.000516 microseconds times 2 equals 1 millisecond, or 1032. So we know the post scaler works. Still something wrong with this frequency. So it says here, 10-to-1 post scaler will count up to 255 10 times. Will that give us 10 milliseconds? Let's see. Well, if we've got 1 millisecond now at 2-to-1, will it give us 10 if you go up to 10? So 10-to-1 post scaler, 1001. So take off 4 spaces, 1, 2, 3, 4. I want a 1, 0, 0, 1, 10-to-1 post scaler. Build and program. Why have we got 5 milliseconds? Going back to this larger view, we've got a 10-to-1 post scaler. Well, that is because we used the 2-to-1 post scaler on our period, and now we are multiplying that period by 10, not our 1 millisecond, multiplying our period there by 10. And what's our period? Our period is 512 microseconds. So 0.0005, if we call it 512, times 10 equals exactly what it says, 5 milliseconds. That's what I put the question mark there. I just threw it in for kicks. So now you're familiar with frequencies and periods and pulse widths, let's get on to an interrupt and setting the interrupt to something we actually want. So let's call it 10 Hertz. So that will give us an interrupt every 10th of a second, 10 Hertz, period of which is 1 divided by 10.1 or 100 milliseconds. So using an 8-bit timer, we know 500,000 kilohertz will not fit into an 8-bit register since it can only hold numbers up to 255. How can we get a longer period if we are already counting as slow as we can, i.e. counting up to 255? Reduce that 255, the period gets faster. So scale the clock down. Okay, let's choose to divide the clock by 4 using the Clock Prescaler. 500,000 divided by 4 equals 125,000 Hertz, 125 kilohertz. It has a period of 0.000008, so it's still 8 microseconds, which is still quite small. We're looking for 100 milliseconds, somewhere in that ballpark. So our desired interrupt is 0.1 of a second. 0.1 divided by that 8 microseconds is 12,500. We could divide that down and use a post scaler. Our maximum post scaler is 16 to 1. So 12,500 divided by 16, 781.25. Ooh, that's not going to fit into a register that holds 255. Okay, let's divide our clock by 8. 500,000 divided by 8, 62,500 Hertz. It has a period of 0.000016 seconds, or 16 microseconds. I'll show it so you're very familiar with finding the period. So 62,500 Hertz, 62,500 Hertz, 1 over X. That's our period. 1, 2, 3, 16 microseconds. So our interrupt is a tenth of a second still. So 0.1 divided by 16 microseconds equals 6,250. 6,250 divided by a maximum post scale value of 16 is 390.625. It still don't fit. I've got a note there. So let's try. A 16 to 1 clock prescaler. That is 500 kilohertz with a period of 2 microseconds. Multiplied by 16 equals 32 microseconds. So you can divide the frequency down, but if you're talking about the period, you multiply the period. Obviously make the period longer. I threw that in there, just, you can do one or the other. So 500 kilohertz with a period of 2 microseconds multiplied by 16, which is the same as dividing the frequency by 16, that gives us a period of 32 microseconds. Sounds better than 2 microseconds, but still on the large side. That's the large number size as opposed to the period, because 32 microseconds sounds still too small. So our next clock prescaler is 32 to 1. And I tried all these. 500,000 divided by 32, 15,625. It has a period of 64 microseconds. But I want milliseconds in the period, not microseconds. 500,000 divided by 64, 7,812.5 Hertz. Period. Period equals no milliseconds, just 128 microseconds. So it's still bad news. Okay, 500,000 divided by 128 must be okay, surely, and that's what I thought when I was doing it. 500,000 divided by 128 is 3,906.25 Hertz, and its period is 256 microseconds. You got to be kidding. And that is seriously what I thought. So I wrote it there. Let me show you. 500,000 Hertz. So we can divide this down first. It's the easiest way. So divided by 128. Surely it's got to be okay. 3,906.25 Hertz. 1 over X. No, 256 microseconds. But we want like a 10 Hertz pulse. Nothing near microseconds. I was shocked, but there you go. The maths doesn't lie. So I skipped the 512 because I figured it was still going to be in the microsecond bracket. I never checked it, but so let's check it now. So 500,000, I'm expecting microseconds. divided by 512 equals 976 Hertz, period of which is, oh, and I'm wrong, that's 1.024 milliseconds. So I possibly could have made do with that. We'll see. You look at the numbers later and you'll see why I just had to jump up. So I moved to 500,000 divided by 1024. That equals 488.28125 Hertz. Wow, it's going really slow now. And that's from 500 kilohertz, so 500,000 hertz to 488. And from this, we can get our 10 milliseconds, which is all the way back up here. Yeah, so I tried all of these. So 500,000 divided by 1024, 488. Wow, it's going really slow now. This has a period of, wait for it, 0.002048, so that's 2 milliseconds. It's OMG, only just reached the slow millisecond bracket, 2.048 milliseconds. So our desired interrupt is 0.1 of a second divided by 2.048 milliseconds equals 48.828125. Round the number up to 49. We need 49 counts of that period to give us our 10 millisecond interrupt lag. So 49 counts of 2048. Let's see. So 0.1, 2, then we've got 2048. So 2 milliseconds times 49 equals 100 milliseconds. If I said 10 earlier, I meant 100. So 100 milliseconds. 1 over x, 9.96 Hertz. That's close enough. So bearing in mind the microcontroller counts from 0 to 255, you have to, and I've done some tests earlier, you do have to reduce that number by 1. So we put a 48 into a timer H register. So in 60 seconds it should count 60 divided by 100 milliseconds equals 600. Or just connect the scope. After all this maths that I've been doing all afternoon just for you guys, so what do I want? I want a 1024 prescaler, 1024, so that 1010, so knock off 4, 1, 2, 3, 4, 1010, so we've got a 1024 to 1 on the prescaler. We're doing nothing with the post scaler. Actually, yes we are. We're putting it back to nothing. That was just a demonstration earlier. So make sure, yeah, that's still set. We go up to our timer interrupt. So from this 255, we want 48, 48 here, 48, and I could set the display, which I have done earlier, uncomment these, build and program. So 48, 48, 1010 on the prescaler, clock prescaler, not post scaler. No post scaling. Let's look at the scope. Also, I need to bring the time base in a bit. Now, in fairness to Keysight, I haven't used this bench view in, well, years, and it said there was an update, but it was taking so long to download. I turned it off twice because I couldn't do this video. If I click on that, oh look, it says new applications available for download, but it took so long, it held me up, I couldn't do the video. So if I go single capture, will it give, oh good, it's given me a result. There we go, so we've got 48 in the timer high register. Yeah, we rounded it down from 49 to 48. Yeah, so we initially rounded this figure up. So 100 milliseconds divided by 2.048 milliseconds equals 48.82. So it's natural to round that up to 49. But then you've got to take into account the timer 0, or the timer increments from 0 to 1. Not like you can on your figures, you start at 1. The timer starts at 0. So you've got to account for that. So drop the number by 1. So we put 48 in the timer high register. It's counting 49 counts of 2 milliseconds to give us our approximate 100 milliseconds, 0.1 of a second. So if I said 10 milliseconds earlier, I meant 100 milliseconds. So I could show you on the screen, but you don't need to see my OLED screen counting up to 600. Just back to the scope. So we've got a pulse width of 101.54 milliseconds, which is, it's good enough considering that we're scaling the clock down by 1024 times, and it's not factory calibrated. It's just an internal oscillator that we can select with a couple of numbers. It's really great. But you can see the work trying to get a fast oscillator down to something manageable. So if you need a very fast interrupt, it's really easy. You don't need to scale anything down. So finally, it's this frequency bit here. Our port, or my port, RH6, is turning on for 100 milliseconds. The next time we get an interrupt flag, the port is inverted to an off. It says 100 milliseconds on, 100 milliseconds off, 100 on, 100 off. But the scope is seeing this bit here and this bit here as one part of the frequency there to there. But in reality, on the chip, we are not outputting like half that frequency, we're outputting a whole pulse width, and so the scope is effectively halving that frequency, just so you understand that. So initially, if you look at the pulse width, the width is correct, but the frequency is wrong. And that's, we're not outputting like a PWM. We would turn the port on for 50 milliseconds, then off for 50. That would then give us the correct frequency. But we're turning the port on for the whole duration, 100 milliseconds. Then it gets inverted for 100, back on for 100. So the scope, as I say, to reiterate, is seeing that as the frequency. But that is not our internal frequency in the chip. And you can see the frequency is defined there by the pulse width in our chip, not on this scope. It's just something you have to be aware of and something to watch out for. Obviously, if you're driving PWM, you won't have this issue. So I'll leave you with the final look at the display, but counting to 3,500,000. I'll use the FOSC divided by 4. So that's 64 million divided by 4, says 16 megs. 16, 1, 2, 3, 4, 5, 6, 1 over x. That's our period. 1, 2, 3 milliseconds. 1, 2, 3 microseconds. So that's 62.5 nanoseconds period for a 16 meg clock. That's pretty fast. So put that into memory. So 256 times memory recall equals our effective frequency, since the timer is counting to 255, is 1 millisecond, 16 microseconds. So it's going to count 16 microseconds 256 times, get up to 3,500,000 and stop. So hopefully now you know everything there is to know about frequencies, periods, pulse width, and certainly timers, and finding specific clocks to suit your needs. Please click like if you liked it or you learned something, or leave a comment. And thanks for watching. Oh, not bad. Thanks for watching.